Good evening. It's 6 p.m. I've been out shopping a little bit more, so I start to get tired. I want to buy more cola for the weekend. Let's read about the transistors. I will try to make a video about it in my language Danish. Now buy little snacks, pork snacks, candy, biscuits, and one more can of chili con carne. Og de buy later, but not buy now. So I like to go to my bed for real, because I'm freezing a little bit. I like to take this shorts off. I will do it because I only have underwear. I will do it behind my camcorder. Like now. This I think it's not labeled, so I need 20 seconds to get to my bed. Maybe I should change my glasses. No.
Transistor. For other uses, see transistor, disambiguation. A transistor is a semiconductor device used to amplify or switch electrical signals and power. It is one of the basic building blocks of modern electronics. It is composed of semiconductor material, usually with at least 3 terminals for connection to an electronic circuit. A voltage or current applied to one pair of the transistor's terminals controls the current through another pair of terminals. Because the controlled output power can be higher than the controlling input power, a transistor can amplify a signal. Some transistors are packaged individually, but many more in miniature form are found embedded in integrated circuits. Because transistors are the key active components in practically all modern electronics, many people consider them one of the 20th century's greatest inventions. Physicist Julius Edgar Lilienfeld proposed the concept of a field effect transistor, FET, in 1926, but it was not possible to construct a working device at that time. The first working device was a point contact transistor invented in 1947 by physicists John Bardeen, Walter Brattain, and William Shockley at Bell Labs. The three shared the 1956 Nobel Prize in Physics for their achievement. The most widely used type of transistor is the metal oxide semiconductor field effect transistor, MOSFET, invented by Mohammed M. Attallah and Dewan Khan between 1959 and 1960 with their team at Bell Labs. Transistors revolutionized the field of electronics and paved the way for smaller and cheaper radios, calculators, computers, and other electronic devices. Most transistors are made from very pure silicon, and some from germanium, but certain other semiconductor materials are sometimes used. A transistor may have only one kind of charge carrier in a field effect transistor, or may have two kinds of charge carriers in bipolar junction transistor devices. Compared with the vacuum tube, transistors are generally smaller and require less power to operate. Certain vacuum tubes have advantages over transistors at very high operating frequencies or high operating voltages, such as traveling wave tubes and gyrotrons. Many types of transistors are made to standardized specifications by multiple manufacturers. History, edit. Main article, History of the Transistor. The thermionic triad, a vacuum tube invented in 1907, enabled amplified radio technology and long-distance telephony. The triad, however, was a fragile device that consumed a substantial amount of power. In 1909, physicist William Eccles discovered the crystal diode oscillator. Physicist Julius Edgar Lilienfeld filed a patent for a field effect transistor, FET, in Canada in 1925, intended as a solid-state replacement for the triad. He filed identical patents in the United States in 1926 and 1928. However, he did not publish any research articles about his devices, nor did his patents cite any specific examples of a working prototype. Because the production of high-quality semiconductor materials was still decades away, Lilienfeld's solid-state amplifier ideas would not have found practical use in the 1920s and 1930s, even if such a device had been built. In 1934, inventor Oscar Hale patented a similar device in Europe. Bipolar transistors, edit. Further information, point contact transistor and bipolar junction transistor. From the 17th of November to the 23rd of December, 1947, John Bardeen and Walter Brattain at NTS Bell Labs in Murray Hill, New Jersey, performed experiments and observed that when two gold point contacts were applied to a crystal of germanium, a signal was produced with the output power greater than the input. Solid-state physics group leader William Shockley saw the potential in this, and over the next few months worked to greatly expand the knowledge of semiconductors. The term transistor was coined by John R. Pierce as a contraction of the term transistance. According to Lillian Hodison and Vicky Deitch, Shockley proposed that Bell Labs' first patent for a transistor should be based on the field effect and that he be named as the inventor. Having unearthed Lilienfeld's patents that went into obscurity years earlier, lawyers at Bell Labs advised against Shockley's proposal because the idea of a field effect transistor that used an electric field as a grid was not new. Instead, what Bardeen, Brattain, and Shockley invented in 1947 was the first point contact transistor. To acknowledge this accomplishment, Shockley, Bardeen and Brattain jointly received the 1956 Nobel Prize in Physics for their researches on semiconductors and their discovery of the transistor effect. Shockley's team initially attempted to build a field effect transistor, FET, by trying to modulate the conductivity of a semiconductor, but was unsuccessful, mainly due to problems with the surface states, the dangling bond, and the germanium and copper compound materials. Trying to understand the mysterious reasons behind this failure led them instead to invent the bipolar point contact and junction transistors. In 1948, the point contact transistor was independently invented by physicists Herbert Matter and Heinrich Welker while working at the company Des Frames et Signaux Westinghouse, a Westinghouse subsidiary in Paris. Mater had previous experience in developing crystal rectifiers from silicon and germanium in the German radar effort during World War II. With this knowledge, he began researching the phenomenon of interference in 1947. By June 1948, witnessing currents flowing through point contacts, he produced consistent results using samples of germanium produced by Welker, similar to what Bardeen and Brattain had accomplished earlier in December 1947. Realizing that Bell Labs scientists had already invented the transistor, the company rushed to get its transistron into production for amplified use in France's telephone network, filing his first transistor patent application on the 13th of August 1948. The first bipolar junction transistors were invented by Bell Labs' William Shockley, who applied for patent 2,569,347 on the 26th of June 1948. On the 12th of April 1950, Bell Labs chemists Gordon Teal and Morgan Sparks successfully produced a working bipolar NPN junction amplifying germanium transistor. Bell announced the discovery of this new sandwich transistor in a press release on the 4th of July 1951. The first high-frequency transistor was the surface barrier germanium transistor developed by Philco in 1953, capable of operating at frequencies up to 60 MHz. They were made by etching depressions into an N-type germanium base from both sides with jets of indium 3-sulfate until it was a few 10,000ths of an inch thick. Indium electroplated into the depressions formed the collector and emitter. AT&T first used transistors in telecommunications equipment in the number 4 AM toll crossbar switching system in 1953, for selecting trunk circuits from routing information encoded on translator cards. Its predecessor, the Western Electric number 3 AM photo transistor, read the mechanical encoding from punched metal cards. The first prototype pocket transistor radio was shown by Intermet Hall, a company founded by Herbert Mater in 1952, at the International Funkausstellung Düsseldorf from the 29th of August to the 6th of September, 1953. The first production model pocket transistor radio was the Regency TR1, released in October, 1954. Produced as a joint venture between the Regency Division of Industrial Development Engineering Associates, IDEA and Texas Instruments of Dallas, Texas, the TR1 was manufactured in Indianapolis, Indiana. It was a near pocket-sized radio with 4 transistors and 1 germanium diode. The industrial design was outsourced to the Chicago firm of Painter, Teague and Peter Till. It was initially released in one of 6 colors: black, ivory, mandarin red, cloud gray, mahogany and olive green. Other colors shortly followed. The first production all-transistor car radio was developed by Chrysler and Philco corporations and was announced in the 28th of April, 1955, edition of the Wall Street Journal. Chrysler made the Mopar Model 914HR available as an option starting in fall 1955 for its new line of 1956 Chrysler and Imperial cars, which reached dealership showrooms on the 21st of October, 1955. The Sony TR-63, released in 1957, was the first mass-produced transistor radio, leading to the widespread adoption of transistor radios. 7 million TR-63s were sold worldwide by the mid-1960s. Sony's success with transistor radios led to transistors replacing vacuum tubes as the dominant electronic technology in the late 1950s. The first working silicon transistor was developed at Bell Labs on the 26th of January, 1954, by Morris Tannenbaum. The first production commercial silicon transistor was announced by Texas Instruments in May, 1954. This was the work of Gordon Teal, an expert in growing crystals of high purity, who had previously worked at Bell Labs. Field effect transistors, edit. Main article, field effect transistor. The basic principle of the field effect transistor, FET, was first proposed by physicist Julius Edgar Lilienfeld when he filed a patent for a device similar to MESFET in 1926, and for an insulated gate field effect transistor in 1928. The FET concept was later also theorized by engineer Oscar Hale in the 1930s and by William Shockley in the 1940s. In 1945 JFET was patented by Heinrich Welcker. Following Shockley's theoretical treatment on JFET in 1952, a working practical JFET was made in 1953 by George C. Dacey and Ian M. Ross. In 1948, Bardeen patented the progenitor of MOSFET, an insulated gate FET, IGFET, with an inversion layer. Bardeen's patent, and the concept of an inversion layer, forms the basis of CMOS technology today. MOSFET, MOS transistor, edit. Main article, MOSFET. In the early years of the semiconductor industry, companies focused on the junction transistor, a relatively bulky device that was difficult to mass produce, limiting it to several specialized applications. Field effect transistors, FETs, were theorized as potential alternatives, but researchers could not get them to work properly, largely due to the surface state barrier that prevented the external electric field from penetrating the material. In 1957, Bell Labs engineer Mohammed Attallah proposed a new method of semiconductor device fabrication, coating a silicon wafer with an insulating layer of silicon oxide so electricity could overcome the surface state and reliably penetrate to the semiconducting silicon below. The process, known as surface passivation, became critical to the semiconductor industry, as it enabled the mass production of silicon integrated circuits. Building on the method, he developed the metal oxide semiconductor, MOS, process, and proposed that it could be used to build the first working silicon FET. Attallah and his Korean colleague Da-Won Kang developed the metal oxide semiconductor field effect transistor, MOSFET, or MOS transistor, in 1959, the first transistor that could be miniaturized and mass-produced for a wide range of uses. In a self-aligned CMOS process, a transistor is formed wherever the gate layer, polysilicon or metal, crosses a diffusion layer. With its high scalability, much lower power consumption, and higher density than bipolar junction transistors, the MOSFET made it possible to build high-density integrated circuits, allowing the integration of more than 10,000 transistors in a single IC. CMOS, complementary MOS, was invented by Chitang Sar and Frank Wanlas at Fairchild Semiconductor in 1963. The first report of a floating gate MOSFET was made by Da-Won Kang and Simon S. Zeddy in 1967. A double-gate MOSFET was first demonstrated in 1984 by Electrotechnical Laboratory researchers Toshio Sakagawa and Yutaka Hayashi. FIN-FET, Fin field effect transistor, a type of 3D non-planar multigate MOSFET, originated from the research of Dai Hisamoto and his team at Hitachi Central Research Laboratory in 1989. Importance, edit. Because transistors are the key active components in practically all modern electronics, many people consider them one of the 20th century's greatest inventions. The invention of the first transistor at Bell Labs was named an IEEE milestone in 2009. Other milestones include the inventions of the junction transistor in 1948 and the MOSFET in 1959. The MOSFET is by far the most widely used transistor, in applications ranging from computers and electronics to communications technology such as smartphones. It has been considered the most important transistor, possibly the most important invention in electronics, and the device that enabled modern electronics. It has been the basis of modern digital electronics since the late 20th century, paving the way for the digital age. The U.S. Patent and Trademark Office calls it a groundbreaking invention that transformed life and culture around the world. Its ability to be mass-produced by a highly automated process, semiconductor device fabrication, from relatively basic materials, allows astonishingly low per transistor costs. MOSFETs are the most numerously produced artificial objects in history, with more than 13 sextillion manufactured by 2018. Although several companies each produce over a billion individually packaged, known as discrete, MOS transistors every year, the vast majority are produced in integrated circuits, also known as ICs, microchips, or simply chips, along with diodes, resistors, capacitors and other electronic components, to produce complete electronic circuits. A logic gate consists of up to about 20 transistors, whereas an advanced microprocessor, as of 2022, may contain as many as 57 billion MOSFETs. Transistors are often organized into logic gates in microprocessors to perform computation. The transistor's low cost, flexibility and reliability have made it ubiquitous. Transistorized mechatronic circuits have replaced electromechanical devices in controlling appliances and machinery. It is often easier and cheaper to use a standard microcontroller and write a computer program to carry out a control function than to design an equivalent mechanical system. Simplified operation, edit. A transistor can use a small signal applied between one pair of its terminals to control a much larger signal at another pair of terminals, a property called gain. It can produce a stronger output signal, a voltage or current, proportional to a weaker input signal, acting as an amplifier. It can also be used as an electrically controlled switch, where the amount of current is determined by other circuit elements. There are two types of transistors, with slight differences in how they are used. One, a bipolar junction transistor, BJT, has terminals labeled base, collector and emitter. A small current at the base terminal, flowing between the base and the emitter, can control or switch a much larger current between the collector and emitter. One, a field effect transistor, FET, has terminals labeled gate, source and drain. A voltage at the gate can control a current between source and drain. The top image in this section represents a typical bipolar transistor in a circuit. A charge flows between emitter and collector terminals depending on the current in the base. Because the base and emitter connections behave like a semiconductor diode, a voltage drop develops between them. The amount of this drop, determined by the transistor's material, is referred to as VBE. Base emitter voltage. Transistor as a switch, edit. Transistors are commonly used in digital circuits as electronic switches which can be either in an on or off state, both for high-power applications such as switched-mode power supplies and for low-power applications such as logic gates. Important parameters for this application include the current switched, the voltage handled, and the switching speed, characterized by the rise and fall times. In a switching circuit, the goal is to simulate, as near as possible, the ideal switch having the properties of an open circuit when off, the short circuit when on, and an instantaneous transition between the two states. Parameters are chosen such that the off output is limited to leakage currents too small to affect connected circuitry. The resistance of the transistor in the on state is too small to affect circuitry, and the transition between the two states is fast enough not to have a detrimental effect. In a grounded emitter transistor circuit, such as the light switch circuit shown, as the base voltage rises, the emitter and collector currents rise exponentially. The collector voltage drops because of reduced resistance from the collector to the emitter. If the voltage difference between the collector and emitter were zero, or near zero, the collector current would be limited only by the load resistance, light bulb, and the supply voltage. This is called saturation because the current is flowing from collector to emitter freely. When saturated, the switch is said to be on. The use of bipolar transistors for switching applications requires biasing the transistor so that it operates between its cutoff region in the off state and the saturation region, on. This requires sufficient base drive current. As the transistor provides current gain, it facilitates the switching of a relatively large current in the collector by a much smaller current into the base terminal. The ratio of these currents varies depending on the type of transistor, and even for a particular type, varies depending on the collector current. In the example of a light switch circuit, as shown, the resistor is chosen to provide enough base current to ensure the transistor is saturated. The base resistor value is calculated from the supply voltage, transistor CE junction voltage drop, collector current, and amplification factor beta. Transistor as an amplifier, edit. The common emitter amplifier is designed so that a small change in voltage, VIN, changes the small current through the base of the transistor whose current amplification combined with the properties of the circuit means that small swings in VIN produce large changes in VOUT. Various configurations of single transistor amplifiers are possible, with some providing current gain, some voltage gain, and some both. From mobile phones to televisions, vast numbers of products include amplifiers for sound reproduction, radio transmission, and signal processing. The first discrete transistor audio amplifiers barely supplied a few hundred milliwatts, but power and audio fidelity gradually increased as better transistors became available and amplifier architecture evolved. Modern transistor audio amplifiers of up to a few hundred watts are common and relatively inexpensive. Comparison with vacuum tubes, edit. Before transistors were developed, vacuum, electron, tubes, or in the UK thermionic valves or just valves, were the main active components in electronic equipment. Advantages, edit. The key advantages that have allowed transistors to replace vacuum tubes in most applications are 1. No cathode heater, which produces the characteristic orange glow of tubes, reducing power consumption, eliminating delay as tube heaters warm up, and immune from cathode poisoning and depletion. 2. Very small size and weight, reducing equipment size. 3. Large numbers of extremely small transistors can be manufactured as a single integrated circuit. 4. Low operating voltages compatible with batteries of only a few cells. 5. Circuits with greater energy efficiency are usually possible. 4. Low power applications, for example, voltage amplification, in particular, energy consumption can be very much less than for tubes. 6. Complementary devices available, providing design flexibility including complementary symmetry circuits, not possible with vacuum tubes. 7. Very low sensitivity to mechanical shock and vibration, providing physical ruggedness and virtually eliminating shock-induced spurious signals, for example, microphonics in audio applications. 8. Not susceptible to breakage of a glass envelope, leakage, outgassing, and other physical damage. Limitations, edit. Transistors may have the following limitations. 1. They lack the higher electron mobility afforded by the vacuum of vacuum tubes, which is desirable for high power, high-frequency operations such as that used in some over-the-air television transmitters and in traveling wave tubes used as amplifiers in some satellites. 2. Transistors and other solid-state devices are susceptible to damage from very brief electrical and thermal events, including electrostatic discharge in handling. Vacuum tubes are electrically much more rugged. 3. They are sensitive to radiation and cosmic rays. Special radiation-hardened chips are used for spacecraft devices. 4. In audio applications, transistors lack the lower harmonic distortion, the so-called tube sound, which is characteristic of vacuum tubes, and is preferred by some. Types, edit. Classification, edit. This section needs additional